All right. Let us first to talk a little bit about linear non-homogeneous systems. Uh, Here is an example from the previous lecture. Hope it is familiar. Right. So here there are three tanks, and there are some tubes. So the water is flowing between the tanks and in the tanks and out of the tanks, and the water is with sugar. And well, we have a system of differential equations that models the amount of sugar in each tank at every point. So this was in the last lecture. What I want to do is, please notice that there is kind of an open-ended question here about what kind of properties will the metrics of such a model always have. If you have some ideas, you can share your properties via comments to this YouTube video. But anyway, let me continue um, uh, finding the equilibrium solution, so the critical point of this system. Okay, so and for an equilibrium solution, we must have so basically we need to have that dx dt must be 0, right? So for an equilibrium solution, so in order to find equilibrium solutions, we need to equate the right hand side of the system to 0. So in this case, there are three variables, and by doing this, we are going to get a system of differential equations, well, of linear equations. Well, and suppose that this is the vector that I'm going to denote by b, right? So, and if this is x, and the matrix of the system is A, then in the matrix form, the linear system of equations is ax equals minus b, right? Because it is ax plus b equals 0, so I'm going to move b to the right hand side. Well, then I have solved it in MATLAB, and here is the approximate solution. So in other words, what we have is that this a times this vector a x naught is minus b. Okay, so let me continue. So now let me introduce a substitution, right? So I'm going to make a substitution. I'm going to introduce new dependent variables by writing that y is x minus this equilibrium solution. Or equivalently, x is y plus the equilibrium solution. Well, the question is how does the system of differential equations change? And basically, of course, so notice that y differ from x by adding a constant. So dy dt is going to be the same as dx dt, because when you differentiate a constant is 0. So let me write it somewhere here, so that dx dt, well, equals dy dt. Well, I'm sorry, I'm recording this lecture in my office, so my touch screen is not so good as the recording studio, but unfortunately the recording studio was fully booked, so I have to do it in my office. Well, anyway, I hope it's not too bad. So now this is just dy dt. Now this is a, this is y, and this is our vector x naught, and this is our vector b from the previous well. So what we have is that dy dt equals a times y plus a times x naught plus b. But then recall that this vector x naught was found from the condition that a x naught is actually minus b. So ax naught plus b is going to be 0, and therefore the remaining system of differential equations is just dy dt equals ay. So here is the answer. So in other words, by making the substitution, we kind of eliminated the constant term in the linear system. So that's the main achievement here is that we have eliminated the constant term. All right, now to understand stability of the resultant system, we need to find eigenvalues. Well, and the first step to find the eigenvalues is to write the characteristic polynomial. So in this case, so the characteristic polynomial is determinant, let me write it here, determinant of A minus Ri. So in other words, you take the matrix A, you subtract R from on the main diagonal, and you compute the determinant of the resulting expression, and then you're going to get the characteristic polynomial. Well, asymptotic stability, as we learned the last week, happens if and only if all the eigenvalues have negative real part. So in other words, we have this polynomial, and the question is it true that all the roots have negative real part? Well, and in algebra, there is a special theorem that allows us, by just looking at a polynomial, to answer this question, whether or not all its roots have negative real part. It's called the Routh-Hurwitz criterion. To be honest, I don't really know how to prove it. It's just a theorem that, well, I know that there is such theorem, so if you're interested, you are welcome to read Wikipedia about this. So this Routh-Hurwitz criterion is about this. So for cubic polynomials, it means that we take the coefficient at r squared, the coefficient at r, multiply together, times, and then we take the coefficient at r cubed, the constant term, take together, times, and, well, the product of the first two must be bigger than the product of the second two. So here it is true, and which means that equilibrium position is asymptotically stable. Well, further, this kind of poses some interesting questions, and they happen to be very challenging, and they're sort of like in math Olympiads. So I recommend that if you like challenge, to try to solve them by yourself. So the first problem is that if the real part of every root is negative, then all coefficients are positive. And then if all roots are real and all coefficients are positive, then all roots are actually negative. Right? So that's the first problem. And the second problem is about the fact that if roots are complex, then it doesn't hold anymore. So come up with a specific monic polynomial where all coefficients are strictly positive, right? But some of its roots have positive real part. All right, so now let me finish the example, right? So we can calculate the actual eigenvalues. So they happen to be real numbers, and they happen to be negative real numbers. Which means that the equilibrium position is going to be sort of a three-dimensional nodal sink, right? So there's going to be three eigendirections, and along eigendirections, well, I mean, all the trajectories are going to converge towards the equilibrium, but they sort of are going to align along one eigendirection near the equilibrium and along another one far from the equilibrium. And then if you want to solve it, here is the solution. And now it's time to stop and do the first quiz.